Good afternoon, everyone. Uh, in the last class, I discussed you regarding pharmacokinetics, right? I discussed you regarding pharmacokinetics, that is PK. So you learn different definitions, right? What do you mean by pharmacokinetics and clinical pharmacokinetics and population pharmacokinetics likewise. So generally, what do you mean by pharmacokinetics? The kinetics which will be denoting you ADME mechanisms. That's what these are called as KADME, right? So this is what we learned in the last class. And one more important one, we already know the relationship between the plasma drug concentration versus time. Plasma drug concentration versus time curve. So we already learned this curve. What about MEC, MSC, absorption phase, elimination phase? Okay, so this is all we learned in the last class. And in this class, I'm going to tell you about order of reactions. So in your syllabus, you have two different kinds of order of reactions are there. Zero order and first order. So in that, I already told you this zero order reactions in the last class, but I did not explain you the what is the derivation of this zero order reaction. So now I'm going to explain you the derivation part of zero order reactions in this class. Okay, so you already know everyone knows this basic equation, right? Dc by dt is equals minus kCn. Your dc by dt is denoting you as order of reaction, sorry, the rate of reaction, the rate of reaction. This is nothing but dc by dt, and small n here, it is representing you the order of reaction. So you just remember these two terms while reading this zero order and first order. dc by dt is rate of reaction and small n is the order of reaction. So the next part, you have only zero order and first order and mixed order also. So you already know this dc by dt is equals minus k0 into c0, right? So now I am going to tell you the derivation part, how you will get this equation. So here I am writing you the derivation part. Everyone has to write it down. So what is the general equation, ma? dc by dt is equals minus k c to the power of n. Then what do you mean by negative sign? Negative sign indicated here the decreasing of plasma drug concentration with the time. See here, every graph is showing like this when you plot the graph between time versus concentration. So what does it mean? There is a decrease of plasma drug concentration with increasing the time we are observing here. So that's what the negative sign is indicating, decreasing the concentration with increasing the time. So the n is for order of reaction. If it is zero order, it is 0. If it is first order, it will be 1. So likewise, this is the major basic equation you have to remember for calculating zero order kinetics and first order kinetics. For zero order, next equation will be dc by dt is equals minus k naught c naught. Sima. Okay, K0, C0 because it is zero order. So when you integrate the above equation, okay, when you integrate the above equation, it will be integration from 0 to C. dc is equals minus K0 integration from 0 to T dt. See ma here, dc by dt is equals minus k0 c0, right? These two are representing your zero order. When you integrate this equation, you will get integration from 0 to c and here 0 to t. So this is a constant, it will be always apart from this integration symbol, right? So then next you have Next you have rearrangement of this integrated equation. Rearrangement. See ma here. Rearrangement of this integrated equation. So how you will get here? C0 minus C is equals minus K0 into T. So after removing this integration, here it will be T. See here minus K0 T. And here C0 minus C. Then C is equals to C0 minus K0 T. This is the final equation for your zero order rate of reaction. So here, what do you mean by C naught? C naught is the concentration of the drug at time t. Sorry, time 0. See ma here. C0 is the C0 is the concentration of the drug at time 0. That means the initial concentration, initial plasma drug concentration, okay, at time 0. So both are initial. So that's what these two are zeros. And what do you mean by C? This is the plasma drug concentration at time t. Plasma drug concentration at time t. That is nothing but C. Okay. So then you need to calculate zero order half-life. See ma, next one is zero order half-life. See everyone, the time required for 50% of the drug to be degraded. So then T will be T half. Then C is equals to C0 by 2. So the time to degrade the drug 50%, that is nothing but T half. Sorry, zero order T half, right? So T will be T half, C is C0 by 2. So the equation is C is equals to C0 minus K0 T, right? This is you know. So then C will become C0 by 2. Then it is equals to C0 minus K0 into T half. See, you never find out this derivation, so you have to write it ma. When they will ask 10 marks, 7 marks like that, you have to write the derivation part in your exam. That's why I'm telling you. Okay, so instead of C, you have to write C0 by 2, then C0 is as it is C0, K0, T half, right? So then C0 is equals to 2 into C0 minus K0 into T half. See here, what you have to here, you just take it out these two and then C0 minus K0 T half. Here C0 is as it is. Then T half is equals, you just take it out this T half to this part. Then T half is equals 1 by 2 into C0 by K0. 1 by 2 into C0 divided by K0. When you bring it out, this T half to this part. Okay. Half into C0 by K0. 1 by 2, I will write it as 0.5. 0.5. Okay. So that's why your final equation for this zero order T half is T half is equals to 0.5 C0 by K0 or C0 divided by 2K0. This is the T half-life for zero order kinetics. So remember it ma, 0.5 C0 divided by K0. So how you will get this equation? From this derivation. Okay. So then first order reaction. See, what is the difference between 0 and first? 0 and here it is first order. So first order is concentration dependent. That is the first point. And zero order is concentration independent. And in case of zero order, your small n is equal to 0. Here, your small n is equals to 1. Small n is order of reaction. Okay. Small n is order of reaction. So you just see how the first order kinetics will be. If n is equals to 1, dc by dt is equals to minus k into c. What is the general equation? What is the basic equation? dc by dt is equals to minus k c to the power of n. This is the basic equation, right? So here in case of first order kinetics, dc by dt is equals to minus k1 c to the power of 1. Sorry, c to the power of 1. So you can write it k into c. Okay, that's why dc by dt is equals to k into c. So this is the equation for first order kinetics. So k is first order rate constant in time inverse per hour, and the rate of first order reaction is directly proportional to the concentration. See ma here. So your first order reaction is directly proportional to the concentration. See, rate of reaction is proportional to the concentration. So that's why the first order reactions will be concentration dependent. So that is, greater the concentration, faster the reaction. So this is of first order kinetics. And one more important thing, and here when you observe this graph will be plotted between the concentration of the drug and rate of the reaction, dc by dt. So how it will be? You will get some straight line. So here it is slope, that is minus k, minus k. In case of zero order, your slope will be minus k naught. Did you observe that? And one more important thing, in case of zero order, you will get the graph like this when you plot the graph between time versus concentration. Have you noticed that? So in case of zero order, when you plot the graph between time versus concentration, here there is an initial plasma drug concentration, and here you will get a slope of minus k naught. And in case of first order, the relationship will be between the plasma drug concentration and the rate of reaction. So why? Because this first order kinetics will be totally dependent upon the drug concentration. That's what you have to plot a graph between the concentration of the drug instead of taking time. Did you notice this observation? Here it will be straight line, and here also it will be straight line. Only the difference is some concentration is in first order, and here in case of time in zero order in case of x-axis. So if you have to notice such kind of points, it is very easy to remember it. And one more important thing, you have to learn the derivation for this first order kinetics. So now the derivation of first order kinetics I am going to explain you. See here. So the first equation is dc by dt is equals to minus k c to the power of 1, right? So dc by dt is equals to minus k into c. So the rearrangement of the above equation. See ma, rearrangement of the above equation, dc is equals to, dc by c is equals to minus k into dt. So you write down dc by c is equals to k into dt. See here. Then you have to integrate the above equation from 0 to c. dc is equals to same like first order, 0 to t into dt. So then after this mark, then you have to take in c minus in c naught is equals to minus k into t. See ma, after getting your constant equation for this is the constant equation for first order reaction. Then after getting rearrangement, you just bring this c to here. then it will be minus k into dt. Then integrate this above equation between the initial concentration and the concentration at time t. See, this is the initial concentration and this is the initial time. So this is the plasma drug concentration at time t. So when you integrate between these two parameters, then you will get an equation in C minus in C naught. That means the concentration of drug at C at time t and initial plasma drug concentration at time 0. Then that is equals minus k, that is a constant, and time t. So then the next equation will be C is equals C naught minus k into t. So this is the first equation number 1. So you just consider this equation number 1. Then you have to write the exponential form for the above equation. Exponential form of the above equation. That is, you have to write the exponential form for equation number 1. Then you will get C is equals C naught into e to the power of minus kt. E is nothing but exponential form, right? So this E is a natural log base. This E is a natural log base. C is equals C0 into e to the power of minus kt. Then in is equals 2.303 log. This is a constant number. When you replace this in the equation, you have to write it down with 2.303 log. Okay. So the equation 1 becomes, log C is equals log of C0 minus k into t divided by 2.303. See here. So your equation of this exponential form will be converted into logarithmic form. Then your equation will become log C is equals log C0 minus kt divided by 2.303. Where you will get this value? By replacing this in, you will get this constant value. Okay. So then this log C is equals, you can write like this, or log C is equals log of C naught minus 0.434 kt. 1 divided by 2.303, you will get a value of 0.434. Remember it, ma. Remember it. While I am explaining, it is very easy. After that, it is tough. See. Log C is equals log C0 minus kt by 2.303. So here, instead of writing kt divided by 303, you can write 0.434 into kt, where you will get 0.434. 1 divided by 2.3 value is 0.434. Okay. So then you have to calculate the half-life, same like zero order kinetics. This is the half-life for first order. Then see here, your C will be C by 2 and T will be T half. Why? Because these are half-lives. So 50% amount of the original drug will be degraded out. That is nothing but half-life. So what is the equation here? Log C, this is the standard equation now. Log C naught minus kt divided by 2.303. So then you can extract this log of C0 divided by C. C Manaresh, C0 divided by C. Then you can write, here T means T half, K into T half. So when you extract this log of C0 divided by C is equals, you can write 2.303 divided by kt half. It will be reversed. See. And then what do you mean by C0 and what do you mean by C? This is the initial drug concentration in the plasma. Suppose you can take always 100% as a 1%. So same like that, you can take initial plasma drug concentration at 100 mg. That is C naught value. Okay. So then this is the initial plasma drug concentration at time 0. That will be 100 mg. And in case of this concentration of drug in the plasma at time t, it will be 50 mg. Then what about your equation? It will becomes log of, write down with me, log of 100 divided by 50, C naught value by C value. Then 2.303 divided by K into T half. Then how much it will be? It will be 2, 50 and 52. So then here it is log 2. Then 2.303 divided by K into T half. Then what is the value of log 2? 0.3010. How the log values will be standard values? Same like that, in case of first order equation derivation, when you remove the in the equation part, you can get 2.303. Same like that. Here it is a standard value. How the log 2 value will be 0.3010? Same like that. So here log 2 value is 0.3010. That is equals to 2.303 by K into T half. Then K into T half is equals 0.693. Is it right? When you 0.3010 is equals 2.303 divided by KT half. When you extract this KT half to the left hand side, then it is equal 0.693. So you will get the multiplication here. This is what? 0.693. Then T half is equal, how much it will be? 0.693 divided by K. K or K1, whatever it is. Okay. So this is the T half for first order half-life. You can remember this equation throughout your pharmacokinetics topic. T half is equals 0.693 by K. Just write the derivation, depends upon your marks. Okay. So this is what the first order kinetics as well as zero order kinetics along with their half-lives. And see here in this graph, yes, after rearrangement and integration of the equation, your final equation of first order kinetics is this. Log C is equals log C naught minus KT divided by 2.303. Then a semi-logarithmic plot of above equation will give a straight line. See ma, here I will show you how the semi-logarithmic graph will be. It will give slope of minus K divided by 2.303. In case of first order kinetics, your slope will be K, minus K, right? So here, if you plot this graph in semi-logarithmic graph, that will be minus K 2.303. And y-intercept is log of C naught. So you just remember only one thing. In case of zero order kinetics, these will be plain C naught or C values. And in case of first order, those are of logarithmic values, log C and log C naught. These will be comes in first order kinetics. And then the first order process is also called as mono exponential rate process. Why? Here you have one exponential form in the equation. Did you observe that? See here. C0 into e to the power of minus kt. That means here it is a mono exponential constant is there. That's what the first order process is also called as mono exponential rate process. Thus, a first order process is characterized by logarithmic or exponential kinetics. That is, constant fraction of the drug undergoes a reaction per unit time. So here your concentration will be dependent upon the unit time. So it will be a constant fraction of the drug concentration at unit time. So this is also called as mono exponential rate process or exponential kinetics or logarithmic kinetics, whatever it is, those are all synonyms for the first order value. So here also same straight line was giving here. So here it is log C naught. This is the same initial plasma drug concentration, and here it will be the slope. Always your slope will be minus k by 2.303. So your slope will be minus k by 2.303. In case of zero order, it will be minus k naught, right? So, and in case of regular Cartesian plot, you can give here, it will give some percentage C, percentage concentration of drug in the plasma, not log C values. That will be given by your regular plot. So that is the major difference of regular plot and semi-logarithmic plot. Semi-logarithmic plot will gives you log C and log C naught values. Okay, so that is the major difference of this normal plot and semi-logarithmic plot. I will send you the pictures of these two graphs. After you just know the difference between these two graphs. I will send you the pics. And what about the first order half-life? That is 0.693 by K. I already told you the derivation, how it will comes. The half-life of first order process is a constant and independent of initial drug concentration. This is the most important words. See, it will be dependent upon the plasma drug concentration, right? But it will be independent of initial drug concentration. That means at zero time. So it will be independent of initial drug concentration. Most of the pharmacokinetic processes like absorption, distribution, elimination will follow the first order kinetics. Why? Why these ADME processes will follow first order kinetics? See, ma'am, if you take a drug, if you take any type of drug, it will be traveled in our body according to its concentration gradient, right? Either it may be undergo absorption, distribution, elimination, whatever it is, the mechanism, right? So it will be traveled in our body according to their concentration gradients. That means the drug will be definitely dependent upon concentration. So if it is concentration dependent, definitely it will follow what? First order kinetics. So all these processes of drug will follow the first order kinetics, concentration dependent kinetics. But only the difference is half-life of the first order process is a constant and it will be independent of initial plasma drug concentration. So it doesn't consider whatever the initial plasma drug concentration. It will be totally independent. Your half-life. Okay, but your first order rate constant is dependent on plasma drug concentration. So these are two major differences between the half-life of first order and normal first order rate constant. So the just now I told you about only zero order and first order. These two only. You have to learn the derivations for order of reaction derivation and half-life derivation. So these two are rate process and order of reaction, which mentioned in your syllabus. So this is about first order and zero order. And you have mixed order kinetics also. So what do you mean by mixed order kinetics? Mixed order, that means it will be mixing. Either it may be follows zero and first or first and zero simultaneously. How it will follow simultaneously? I will tell you later. See first. Sometimes the kinetics of the pharmacokinetic processes fluctuates from predominantly first order to predominantly zero order. That means first it will be dependent upon drug concentration and later it won't be dependent. See, therefore, such kind of kinetics are called mixed order kinetics. So the mixed order kinetics are also called as dose dependent kinetics or non-linear kinetics. Why these are called dose dependent kinetics? See, these are traveling irrespective of their concentrations, right? So sometimes it will follow up to some extent. Suppose the drug biological half-life will be, see here, suppose the drug biological half-life will be 3 hours, right? So up to 1 hour it will dependent upon concentration. That means it will follow some first order kinetics. After first hour it will goes independent, it will traveling independent of concentration. So it will follow zero order. So within this 3 hours it will showing two types of fluctuations here. Sometimes it will be concentration dependent and sometimes it will be concentration independent. That indicates first order and zero order will be mixedly it is showing. So that's why it is called as mixed order kinetics. So in that cases of drugs, you just consider the dose of the drug. Okay. So that is what if the drug will be 10 mg. So if the drug dose will be 10 mg. So this 10 mg will be traveled within this 3.5 hours with irrespective of this concentration of the drug. Did you understand? This 10 mg of the drug will be traveled within this 3.5 hours in our body with irrespective of their concentration. So that's what these are dependent upon the dose with irrespective of their concentrations. That's what these are also called as dose dependent kinetics. And why these are also called as non-linear kinetics? In case of first order or zero order, you can get some linear graph. Okay, so in case of this non-linear, you will not get the graph like this. Why? Because it is showing zero order and first order. So how you will get a linear graph? It is highly impossible. So that's why it is showing non-linear kinetics. So what are the drugs examples behaving these kinds of release pattern? Drug absorption of vitamin C, drug distribution of naproxen, and drug elimination of riboflavin. SEMA, here the mechanisms are different and the drugs are also different. Absorption of vitamin C, distribution of naproxen, and elimination of riboflavin. And non-linearity is usually seen when the pharmacokinetic processes will involves, involves carriers or enzymes which are substrate specific. Okay, so what are the drug products will be substrate specific, that is either of carrier specific or of enzyme specific. These will get saturated at high drug concentrations. So what is our main aim? Either it may be depend upon concentration or independent of concentration. Then you can say that, okay, then you can say that it will follow zero or first order. But some drugs will follow non-linear kinetics. Why? Because those may get saturated at high drug concentrations. So which will be substrate specific with either of enzymes or carriers. So that's why the concentration of the drug will be saturated. So you cannot say that it will be follows first order or it will be follows zero order, right? So how you can explain this kind of kinetics? By using Michaelis-Menten kinetics. He is one of the scientists. He clearly described about non-linear pharmacokinetics, and that non-linear pharmacokinetics topic will be have in your 7th or 8th topic, 6th topic in your syllabus. So when I will tell that topic, I will describe about this Michaelis-Menten kinetics. In this introduction to pharmacokinetics, you just remember up to this points. That's it. Okay.